Okay, homework number 6, Dr. C, problem number 2. So this problem says that you have a ball of mass M attached to a massless rigid rod spinning in a vertical plane. So here's the general situation: massless rod of radius or length L, which will define the radius of the circle, a ball of mass M, okay, that's spinning in a vertical plane at constant speed v. I'll use v for magnitude of velocity, but that's a speed. Okay, and so it's always changing direction, but we don't have to worry about that. Okay, part A says, what's the force in the rod whenever the mass is at the top of the circle? Answer in terms of M, G, V, and L. And the question is, what's the force in the rod? Okay, so this is a Newton's law problem because we're after a force. So what I need to do is draw a force body diagram or a free body diagram. So let me do that. We'll have here's the circle, the path of the mass. The mass is a particle. Draw it any way you want as a particle if you like. There's a radial force due to the rod. Now I don't actually know the direction right now, but the rod can only supply a force. An ideal rod can only supply a force along its length. We won't worry about forces perpendicular to that, at least yet. And we have the force of gravity, which also acts down, so that's just mg. So those are the only two forces acting on my rod. Now I have to pick a direction, and I like to use r hat out, but let me just do something different this time, and we'll say my positive direction for this free body diagram is plus y pointing down, which means pointing towards the center of the circle. Okay, so we also know then that the sums of the external forces, okay, have to be equal to the mass times the acceleration. So we just carry that out and we say, well, what external forces are acting on the mass? And there's the force of the rod, which is in my plus y direction with my arbitrary choice. I could turn it to be wrong, but for now, I've got it in my plus y hat direction, so it's positive. I have mg, which is also in my positive direction. Those have to be equal to mass times the acceleration. And because we're told that it's spinning in a circle at constant speed, then there must be an acceleration, a centripetal acceleration of v squared over L. L is the radius. Normally it's v squared over r. And I can solve this immediately for the requested force of the rod. The force of the rod is just take mg to the other side. I'll factor out an m. V squared over L minus G. So that's the answer to part A, the force of the rod in terms of M, V, L, and G, like we saw up here. Okay, part B. What force is the rod supplying at the bottom of the circle? So I'll draw another free body diagram. I'll have the mass at the bottom of the circle. I'll say, well, there's mg down. There's a rod. And I'll draw arbitrarily the force of the rod pointing up. See if I'm right. And then again, I'll apply Newton's laws at this point of the path and say that at the bottom, I've got the force of the rod. Oh, I've got to also point out what direction I'll pick. Let me just, for fun, pick plus y up here. Okay, it's not just for fun. I know the acceleration is upward direction, but I could have picked either direction and still get the same answer. It would just change the sign of everything in my equation. If I had reversed plus y, kept it the same as I had up here. But I'll do it this way. So the F of the rod is in my positive direction now, but mg is in my negative direction, so that's minus mg. That has to be equal to the mass times the acceleration, but it's going around the circle at constant speed. The acceleration has to be v squared over r towards the center, which is my positive direction. So v squared over L. And so now I can immediately write the force of the rod equals m. Again, take mg to both sides. And now I've got v squared over L plus g. Stopping to think for a moment, I look at the difference between these two. This must always be a positive value because you're adding two positive numbers. This could be positive or negative, depending upon the relative magnitudes of v squared over L compared to G. So that tells me that my choice of the rod's force being down is correct if v squared over L is bigger than G, but it's the reverse of the correct answer if v squared over L is less than G. But there's nothing wrong with that as long as it's a rod. A rod can push out or pull in, unlike a string, which can only pull in. So everything's fine. We can continue on part C. Part C says, like I just said, the force at the bottom is always tensile. The force at the top will switch from tensile to compressive at some particular frequency. What is that frequency? Well, we just said the condition for this term to change signs is when v squared over L minus G equals 0. And that tells me that it will change from a tension to a compression or back again when v equals the square root of GL. Okay, that's a velocity. The question asks, what's the frequency? F, not omega or anything. So I just have to convert velocity to frequency. And remember, the general rule is a t, where t is a period now, just to be perfectly clear. A period of motion is the distance, which is the circular circumference divided by constant speed or constant velocity or speed. So the period equals this. And we also know that frequency, I'll just make sure it's clear, this little f stands for frequency, is 1 over the period. So frequency equals to v over 2 pi r. And so I can write the frequency of this motion, of this critical frequency, v over 2 pi L, because instead of r we have L. Okay, and we have from up here that magic velocity is the square root of GL. Okay, and that's divided by 2 pi L. So I have the square root of L over L and the square root of G, and so the favorite way of writing this is 1 over 2 pi square root of G over L. So this will be the critical frequency. And if it's the mass is spinning faster than this, then in fact the rod will, with v squared over L bigger than G, then there'll be a tension in the rod pulling the mass. And if you're below this frequency, then in fact the rod will have to hold the mass up as it spins around. Okay, it'll be a compressive force on the rod. Okay, so let's continue with part D. Okay, what's the speed of the ball at the top and bottom of the circle, Vt and Vb? Question, what's V top and V bottom in terms of the tension, the mass, L and G? Okay, well, we've sort of done this work already, but we're just asked to phrase it in a different way. Okay, at the top, and you can refer back up to the figure I've got here. At the top, we have tension. Instead of the force of the rod, tension plus mg equals mv top squared over L. Notice it's exactly the same formula I had here, except instead of the force of a rod, okay, it's the tension of the string, because we're replacing the rod with the string. And we're trying to keep a constant tension in it, and that's what the problem statement says, what would happen if you were able to do that and did that. Okay, and so for this to be true, the velocity at the top, we're just rearranging terms. For this to be true, the velocity at the top can multiply both sides by L over m and take the square root, as we have v squared. So we'll have T L over m plus GL. Because when we multiply by m over L, that'll cancel this m and just give us an L. So this is the velocity you need at the top, or you'll have at the top. Okay, if you have a constant tension in the rope and it makes it around. And part E asks you the same question, the minimum speed. Okay, I'm sorry, no, I'm still in part D. Part D says at the bottom, we have to solve for velocity at the bottom. And here we just had T minus mg. Again, what we had up here, except instead of the force of a rod, it's the tension of the string. It has to be equal to mv bottom squared over L. And we can solve that for v bottom equals the square root of TL over m minus GL. So those are the answers for part B. What are the velocities at the top and the bottom in terms of the tension if you have a constant tension and you know the mass and length of the string in G. So one more part, E. E asks you, what's the minimum speed you need at the top so that the ball makes it past at the top without the string collapsing? So you have to translate string collapsing into one of the terms in this expression. And in fact, the conversion is string collapses when the tension equals 0, or goes to 0 if you like, but we'll just plug equals 0 into our equation. So all we have to do here is say, okay, tension goes to 0, the velocity at the top, which is the square root of TL over m plus GL, this goes to 0, square root of GL, done. Okay, that's the minimum speed at the top that you have to have so that the tension will be bigger than or just slightly bigger than 0 at least. That's it.